Hello, students. So we're finally ready to actually talk about our original problem and come up with a solution or a way of explaining why that couldn't be done. Okay, so we have the alternating group, which represents all the positions that we can reach: red, orange, yellow, green, blue, purple, all the positions that we could reach from this, or all the positions that we can get to from here. We started here, and I want to know, can I get from this to this? Which would, if I could get from this to this, then I could get from this to this, right? So can I get from here to here? Well, what I'm going to do is I'm going to write this as a permutation. So let's see what happened here when I move these. So the second block went into the first position. So 2 is going to go to 1, 3 is going to go to 2, 4 is going to go to 3, 5 is going to go to 4, 6 goes to 5, and 1 goes to 6. So I can write that permutation as 1 goes to 6, which goes to 5, which goes to 4, which goes to 3, which goes to 2. So that's how we started the game, and we wanted to get from here to the identity. Now, I know that any permutation is either writable as, well, it's either even or odd, right? Which means it's either writable as an even number of 2 cycles or odd number of 2 cycles. So what is this? Well, we have a special way of writing this, right? This is equal to 2, 3, 2, 4, 2, 5, 2, 6, 2, 1, using that trick I showed you where you take this and then this and then this all the way. Right? Now, of course, in this, we actually apply the 2, 1 first, but our notation-wise, the 2, 3 is on the left. It doesn't matter. This is equal to this, right? Because here, look, 2 goes to 1 and stays 1, so 2 goes to 1. So this does work. 6 goes to 5 because 6 goes to 2, which goes to 5, and so on and so forth. So this does work. How many 2 cycles do I have here? That's an odd number, 5 2 cycles, which means this can never be written as an even number of permutations, and the even permutation as an even number of 2 cycles, so it can never be an even permutation, which means I can never get to the identity, which is even, which means I can never win the game. There's no way, because this initial position is an odd permutation. The odd permutations are the ones for which you cannot win this game, and the even ones are the ones for which you can. And since no permutation is odd or even, we can definitely say that. And since all the moves are even, we can definitely say that. So we're putting all that together. So what do we know? Well, we know why the game is unwinnable. And we could either stop here completely, but you might suspect that the alternating group has more purposes than just this one game. And that is true. So let's try to take a look at that. What's the size of the alternating group? We don't know in general. What are the elements in the alternating group? I mean, we know they're even products, an even number of products of 2 cycles, but once we reduce their form, what do the elements look like? Okay, so these are some good questions. Maybe we'll try this first one. Okay, so every element of AN can be written as A1, A2 through A2n. Instead of saying n is even, I'll just say n is an integer, and I'll do A2n. And what I want to do is I want you guys to consider this map. F from the symmetric group to the symmetric group. And F of sigma is going to be sigma 1, 2. So basically we do 1, 2 first, and then we do the permutation, whatever that permutation is. Okay, now what does F do? Well, F sends, I need a name for the odd permutations, and we're not going to keep this name long term because the odd permutations are not a very useful thing to look at. They do not form a group. But for this example, I'll call them D. No, that's horrible. D stands for the dihedral group. Okay, I'll call them, I hate doing that. I hate using O's because people think they're zeros. I'll call them ON. Not that ON doesn't have another meaning in math, because it does, but whatever. Okay, so F maps the evens to the odds, because if you plug in an even permutation, it's going to take an extra 2 cycle at the end and it's going to toss it on. We're going to get an odd number of 2 cycles in total. And F also sends the odds to evens. Okay, F is a bijection from Sn to Sn. And what do we have to show there? Well, I mean, first of all, if F of sigma equals F of tau, what would that mean? Well, that would mean sigma 1, 2 is equal to tau 1, 2, and we could multiply both of these on the right by 1, 2, which is the inverse of 1, 2, which says that sigma equals tau. So this is actually injective. Injections and surjections, very important, because it's important to know when something is a bijection. But what about showing that it is a surjection? That means every element can be hit by something. Well, I want to find for any sigma, we want a tau so that F of tau equals sigma. Okay, so I want to show, and what is this? Well, that would mean that tau 1, 2 equals sigma. And I have to find tau. So what would tau be? Well, tau would be equal to sigma 1, 2. I just multiplied both sides of these by 1, 2. So tau is going to end up hitting sigma. And for any sigma in Sn, in our permutation group, there is going to be a tau that gets sent to it. So therefore, this is surjective. Okay, so what does that tell me? It tells me that F is a bijection from Sn to Sn. So this is a map which is both onto and one-to-one. So there's a one-to-one course. Well, I don't need to say that. What do I want to say? Okay, so what I want to say is we have a bijection. So it doesn't send two things to the same thing. Everything it sends somewhere else. I mean, two different elements get sent to two different elements. And since we know that F of An equals On, that means each of the elements in An gets sent to a different element of On. No two things go to the same place. So I have some map from the world of An to the world of On, where I can look at the image of An and it's contained inside On. So that means the size of An is less than or equal to the size of On. Okay, but since F of On equals An, I can use the same argument to conclude this. So the even permutations, the number of evens, is less than or equal to the number of odds, and the number of odds less than or equal to the number of evens. So the number of even permutations equals the number of odd permutations. And we'll talk more on size in the next video.